Hello, thank you for the nice announcement. Today we'll be talking about further enhancements of recommender systems using deep learning. First of all, let me say a few words about myself. During, I don't know, professional life circumstances, I started working from an early age, let's say from 17 years of age. Then I worked 10 years as a software web developer, full stack developer, well, that's popular nowadays to name it. And then I switched to strictly, let's say, data science waters, bioinformatics, digital marketing, and now let's say that I'm a data science without domain currently. So let's begin. Recommender systems, I'm not sure how many of you probably already heard one of my few previous talks, not on data science conference, but on previous conferences. I have to make a good intro about the whole thing because I don't want to be too, let's say, advanced of a talk. So you can all, I'm doing my best that all of the people that are listening to my talk experience or have some benefits from it. Okay, recommender systems. Recommender systems are some, let's say, part of data science or our everyday life, and I'm really, let's say, like dealing with them because they are beneficial both to service providers and final users, and they provide us that personalized experience that we are all craving for in each service that we are using. Not to mention the industry, so we have a lot of big names, big companies here. All of them are really heavily reliant on recommender systems one way or the other. These are just figures. They're probably, I don't know, from a few years back, the percentage is probably even higher. So this is some current state. So let's start with the basics, like the types of recommender systems. We have content-based, collaborative-based, and you guessed it, some hybrid models. And usually some hybrid models is something that is, let's say, currently used today. We'll see that as much of this talk is a general story, it's really highly specific about the data set that you are dealing with. So one type of recommender systems will be really beneficial towards one type of data set, and you have to figure out which is which and when to use each of them. Okay, so to make the short intro about recommender systems, and for the people that aren't aware of the peculiarities, content-based recommenders, we can divide them in, let's say, two great parts. Content-based recommenders rely heavily on the properties of an item. So good categorization of that particular item, description, maybe cover photo, it doesn't matter. And the second big thing to remember is that they are independent of users' behaviors. So, for example, if you have some guy that's preferring one type of beer, we can offer a similar product to him. So we are now explaining what does that similar means. Because for that particular item, we have its category, we have some description, we have some cover photo. So it's easily for us, the things that we are taking for granted, to find a similar product or similar type of beer, whether it's, I don't know, an IPA or a lager or you name it, to recommend some similar product. That's cool because we don't have a cold start problem. So immediately when our end user is starting to experience our platform, we can offer him some kind of a recommendation. But the thing that this system is highly lacking is it cannot recommend anything genuinely new, because we are recommending the things that are really similar to that particular thing. Collaborative recommenders, I always like to say that that's if I have to make an analogy, that would be the situation where you are asking your friend for a recommendation about something. So if you have a friend that you're really cool with him, with her, and you can, I don't know, experience similar taste in music, in movies, and there's a really great chance that they can recommend you some, let's say, I don't know, theater show that you would find really beneficial. And if you like that person, if he's your close friend, you will have a greater confidence in that recommendation than in some random people from the street. So that our collaborative recommenders are all about. They generally give better results than content-based, but they are domain-free, so you don't need any kind of specifics about some particular product. You don't need really anything. You just think of it as a great matrix of user-item interaction. So that really big matrix is the collaborative recommenders are all about. But they do suffer from cold start problem. So if you don't have any kind of interaction yet with the system, it's not going to work well. So you guessed it. So some usually content-based recommender systems are used at the early start, and afterwards, when the end user is having more experience with the system, they can benefit from collaborative recommenders. So you probably realize that we have a problem of a sparsity of information. For example, for Amazon, where they have millions of users and dozen millions of items as well, so that there are really small amount of products that we had some sort of experience with. I have explained about the hybrid recommender, some combiner function or weighted product, so we won't go into details. Just to have a quick glance of the rating systems, we do also take that for granted as well. Keep it in mind when you're dealing with your particular data set. So feedback and ratings come in really variety of forms. We can have continuous, discrete, ordinal, binary, unary systems. They're all, you can recognize them in your everyday browsing the web. You experience really each of them. And for the feedback, you already mentioned ratings. Ratings are something that is described as an explicit feedback. And that's the feedback that you're getting. For example, if someone's rating a movie on IMDb, that's an explicit feedback. So they can be both positive or negative, and that's they have a high accuracy of their result, because we are really, really certain that if I gave some film a score of 9, that I really, really like it. And that's about it. But the things that's, let's say, well, missing, lacking, with the explicit ratings, that they are really scarce. So there's really few of them, and it's much more easier to collect various implicit feedbacks in the system. So we can describe what are those implicit feedbacks currently. Okay, browsing a web page, browsing a product, how many seconds have you watched to some particular product, etc., etc. But then again, we have a lot of noise there because, for example, I don't know, we opened up some particular product, or we played a song, and then something caught our attention, and then we strayed away and got back to our computer like 30 minutes later. So there's a lot of noise, and you have to deal with that as well. And this is some sort of, let's say, how's the famous, I don't want to say famous Pareto principle, but for the 20% of products, usually they are getting 80% of your feedback. So those are the like general products. For example, you're coming into a store, or I don't know, some various types of milk, water, bread. That's something that all of us are taking. But the thing that distinguishes us are these long tail niche products that are really have a skewed distribution. For example, someone is liking some specific, I don't know, pesto, or someone is liking some specific type of hummus, and those are the things that are really make difference between each of us. So to go to how are we dealing with both of the content and collaborative, this is just a short summary. So for content-based, we have additional information about about each of the items. So it can be text, video, images as well. And for collaborative-based, we solely rely on user item historical interactions. And we are also using implicit or explicit feedback. Not to go in too much details about content-based and collaborative-based recommenders, let's say that during some, let's say, history in recommender systems, that matrix factorization methods had a really big and major role in dealing with this kind of data. and they're really, let's say, popular even nowadays. I don't say like even nowadays because it's a great tool, it's a good tool, we can use it still, and for really a lot of systems today, we can really benefit from using these systems still. So just to explain it in short detail, the idea is to have to convert this really big sparse matrix of user and movies, so the ratings, we can convert it in the matrix factorization, so a product of two matrices that are of lesser size. Not to go too much into details, we can see that if the C is a number of, it's called latent factors, not to go too much into details about it, we don't have time. But we are aiming for that number of latent factors to reduce our size of the matrices, and the more factors we have, the more accurate will be our final score. And there are really, this is just a few popular matrix factorization algorithms and some directions when to use which of them. And now we are going to, let's say, the main point of our discussion about the deep learning-based recommender models. First, some short intro about okay, I don't need to, make some obvious pluses about the deep learning systems. But in the past few decades, we have witnessed a tremendous success in using deep learning in various applications, such as computer vision and speech recognition. And what is really cool about them, they're introducing non-linearity in our relationship and dealing and modeling our complex problem. And we will see how we can benefit for using in the recommender systems that kind of models. So these are, let's say, some general strengths of deep learning-based models. We have a nonlinear transformation, which is really cool and powerful tool to learn complex underlying explanatory factors. And for we will see afterwards for the recommender systems, they're really fantastic because for the deep learning recommender system, we can use it for sequence modeling. And we can use it for next item prediction or session-based recommendation. And also, it's good flexibility, plethora of frameworks, and good modularization of each of the solutions. Then again, we also have the downside, which are also well known about the deep learning systems. They're pretty much black box and have a limited explainability, but okay, we're really doing our best as a community to ease up that problem. Second problem is that the deep learning systems require large datasets, and which is really, let's say, less of an issue. Less of an issue for the recommender systems because, as we already mentioned, we have explicit and implicit feedback, and for the implicit feedback, we can really have a ton of them. So that's a cool thing about using the deep learning methodology for the recommender systems. And also we have a extensive hyperparameter tuning for each of the models. So let's say to name a few solutions, we'll cover let's say the broader picture of everything. So for content base, we mentioned that we have additional info about each of the items. So we have heterogeneous nature of information, so we have some additional text, image, video, and we can look at it as a resolvement of each problem. We can look as a separate neural building block to solve each of the, let's say, represent text or image or a cover photo or a video. And then afterwards we combine it into some integrative network for giving our final a final rating or evaluation of a particular user item item score. And for, let's say, what's the downside of this kind of modeling? It's costly preprocessing. So each of the problems we really have to do our best to model them. For example, for description of the specific items, we have to do separate keyphrase extraction, topic modeling, etc. And afterwards, we have to maintain each of the modules separately. So the newer-based learning approaches is that we use deep learning as an end-to-end solution. So for those of you that aren't, let's say, familiar with the concept, The idea is so that we just put everything into our network as a input parameter. So for example, for images, text, everything we just put as an input parameter, and we are, hoping for the best that our deep learning model will eventually come to a reasonable understanding of the underlying interaction. And what is really, for example, when I was preparing this, I came across to a really cool, it was I don't know whether it was a faculty project, university project, but the person built a recommender system based only on cover photos of the movies. And for me, if someone asked me or proposed that kind of recommender, I would say, okay, it's not going to work, definitely. I would even bet some money on it, but the guy proved me wrong. And it turned out that it has a really good score. Okay, not to get everyone frightened, but these are some of the architectures that can be used. There's a paper down below, which you can. I will also include. I also included it in the comments at the end of the slide, so you can take a look for the deeper understanding of the model. So for the user item interaction or collaborative filtering, we have two ways of dealing with. So improve the matrix factorization situation. And because of limited, let's say, time scope, there's a factorization machines as well as a natural progress of matrix factorization methodology. We won't go too much into details, but the idea is that all of these are also still linear problems. So we'll do our best to introduce non-linearity to that particular problem solving. So just to remember, we have a user item interaction, and for example, for a specific rating that we are doing, that we are trying to predict, we have a dot product between two vectors, and that's also, let's say, addition and multiplication. So we are still in the linear types of space. And this is some really small example about the limitation of matrix factorization, even on this small model. But okay, someone can discuss whether this is because of the low latent space that we chose. But not to go too much into details, if we take the similarity between the specific users and the items that they are rated, we have a situation that we have, for example, we introduced into our system the fourth user, and considering the scores that he is getting, there are, let's say, two positions that we can put him in this two-dimensional vector representation of the model, and neither of them will represent the current situation because of the similarity, because of the different similarity that particular user will get. Just a second. Yeah, and so we are coming to that situation when we are dealing with. So instead of we still have our input space that is basically the same. So it's here it's binarized. So we have a interaction and it's we used one hot encoding for all of the users and items. So it's a binary vector. We use our latent vector still, so we can produce it using matrix factorization techniques. But we won't predict the final rating with the dot vector product, but we will use our deep neural network for dealing with that situation. So again, for more details, please refer to the paper below. And for what's really interesting about the recommender systems, let's say all of these methods, when I'm, let's say, reading the papers, checking all of them, on one side, I always have okay, this is really a cool idea, this is interesting stuff. I don't know, I would use this or that, or use it in my next project. But then again, I think that there's really many people that already refer to that. Let's say I read it somewhere, I can't remember where. It's really okay, and for us to have a product sense. So if you're developing a product, you really need to know who will be the end user of that product. Or for example, does that particular, I don't know, store, web shop, or some service that you're offering need that kind of level of expertise with the recommender system or anything else that you're building with? So really start small, have some alpha version that is really cool and working, then you can justify your fundings, let's say. So it doesn't matter whether you're in a big company or in a startup. Everywhere data science systems and teams are really small. So like a couple of people, that's about it. So really, we really need to be, you know, both tech savvy and know how to present the end findings and so on and so on. Yeah, not to go too much into details about but what's cool about CNNs, convolution and recurrent neural networks have long exploited the underlying structure in vision and human language. So let's say in computer vision, we exploited the neighborhood pixels. And for the, let's say, language interpretation, we exploited the fact that words that are really, let's say, closer to each other have more reference, and we have some more prediction power towards the next words that are coming up. So the great success that they are having is credited to the concept of parameter sharing. So for one layer of the network, we can share the information for the next, or we have some kind of interaction between the inputs or the inputs and the next output in the network. This is a bit, well, I hope it's not too confusing. But what is the really cool thing that when I was thinking about deep learning based recommender systems, immediately for me it was like, okay, it's cool to use. And we have two really good justification. If we apply our recommender systems to use deep learning methodology, that's cool because we can train it on GPU and not to train it on CPUs and using regular algorithms. And second, I'm always thinking when it's like deep learning recommender or deep learning in general, that it's really, you need to use it for some high-end product. And this is the special occasion when I think that it's not like that, because now we are dealing not only with content or collaborative-based recommender systems, but we are dealing with sessions, click logs. So we'll see that really a lot of real-life recommender systems often rely on short session-based data rather than long user activity. So for example, for sequential modeling, this is, we can take that this is a, I don't know, my purchase history from Amazon, but it's not. These are the things that are purchased in the, it doesn't matter, purchased in the past. And this is something that I'm currently looking at my current session. So does it have any meaning for me to recommend some t-shirts or sneakers? No, it doesn't. So it's better to look like shorter sessions and to find something meaningful for me in that particular niche of products that I'm currently looking. That's one thing. And the other thing is change of interest. So I can switch change of interest. For example, last year I was searching for some climbing shoes, and I don't know, for example, this winter is all about scuba diving. So it's really important for you as a builder of that kind of recommender system to distinguish that change of interest in some purchasing, viewing patterns, and so on and so on. And not to mention, for example, it's really cool for sequential modeling. Any of you that's using Netflix, they have their own algorithm that can distinguish how many users are using the Netflix. For example, for me, it's really cool, let's say, scenario. And this is like a mock-up of that current modeling data flow. So on the left, we will have an input session, which can consist of which user, timestamp of the action. We can have multiple actions, like whether it's a view of some product, a purchase, or add to wish list, etc. And on the other side, we will have a list of outputs. It can be a single output, or it can be a list of outputs, depending what we are trying to do. So for example, if those are like, for example, climbing shoes, it's completely okay for me to offer a list of alternatives to the current climbing shoe that I'm checking. And second, it's completely okay to have a list of complements to that particular product. So if I'm going to, I don't know, scuba diving, if I'm checking mask, it's okay to offer me fins or a weight belt or something similar. And for sequential modeling, we exploit the recurrent neural networks. and they're really highly suitable for sequence modeling, but as it turned out, they suffer from the short-term memory problem. That's why nowadays we have LSTMs and GRUs, which are, let's say, not modern, but subtypes of, or modern versions of recurrent neural networks, and they're created to mitigate the issue. Sorry, just a second. And also, not to go too much into details about the specific functioning, but the idea was to have because the next output for each of the recurrent neural networks, we are using the input from the output from the previous step. And all of those LSTMs and GRUs are trying to keep that information from the first steps not to go somewhere in vain or to become less and less important over time. Yes, and for the closing remarks, probably I already mentioned a few, but all of these algorithms that are currently used, we can really, they're not reserved only for a product item recommendation. They're really cool to model any kind of interaction between various types of objects, not to name a few. I already addressed this issue. It's really, really important because despite the fact that all of us are eager to have really some cool project in your portfolio to do something really cool and new and genuine, it's really okay to use some existing stuff, to adapt it to your current solution, present your results, because that's where you will getting, let's say, low-hanging fruit or 80% of the something that you're building, and then again you will have some common sense baseline for your further development and improvement. Second thing, I was also referring to that. It's a really simple photo. It's really looks like a dumb situation, but it really happened to me not just once. It's really important for us as data scientists to follow your product from start to finish, because you want to know, for example, this is some web shop XYZ, and you have two locations for the recommender. It's really obvious that if it's placed on the bottom place, that it will get less engagement than at the first. And then again, if you're having multiple recommenders, it's also really beneficial to know which one to promote and which to move further down the line. So these are just really like basic things, but you can't imagine the amount of situations that these basic things are happening. So when you're developing something, know who is using it, how it is used, and how you can help out to build the all-around product. So I will end with these additional links, and I hope lots of interesting papers for you to read. And that's about it. Thank you for the attention.
We have time for a couple of questions, literally a couple. Could you please give us some examples for usage of this model in banking environment?
Banking environment. Okay, we will, I think we had some similar talk. Well, any kind of interaction, for example, we can have some interesting new product that our bank is offering, and we want to know which users are really like the best fit for that.
Difference between NBO and this model, if there are any?
Between
NBO and this model.
Sorry, can someone...
So what would be NBO?
I apologize, it sounds familiar, really. Sorry? Next best offer. Ah, well, I don't know. I haven't... Well, there are really, let's say, a lot of models, for example, that can exploit the ranking of the items. For example, we can use the learning to rank a lot of like different algorithms, but I haven't compared them in terms of, let's say, efficiency.
Okay, and the last question was to return the slide with the papers back so that everybody can see them again. Okay. Okay, so that'll be it from Mladen.
Thank you very much.
With certificate.
Thank you, Zoran.